everybody. I have been asked to do a video that sort of summarizes our semester. And I'm doing this unscripted. It's just going to be, unfortunately, full of a lot of ums and ahs. And hopefully it helps. It's going to be lengthy, is my guess. So my apologies for that. I will be as brief as I can be. If you ask what we're going to talk about, I have a list here. As you can see, I've already tried this video 3 times now, and this is the 4th try. But these are the concepts or the topics I'm going to try and discuss. So the first thing that we did was we tried to learn how to visualize our data. And we did that just first of all learning how to just get a count using Jamovi. And that I feel that you probably have a strong grasp on how to do. The parts of our experience that seem to be still bothering people consistently is more about how to develop the hypothesis test and that sort of idea. So I'm going to talk about the visual data that can help us out when it comes to doing the hypothesis test or the confidence interval. Really, those are the things that we do when we're dealing with what's referred to as inferential statistics. You can hear my dog chewing on her ball in the background. So, all right. To do this, and again, my apologies for the ums and the ahs, the clearing of the throat. To do this, I created an artificial data set. So I just went to a Jamovi, and I put in column A Cokes and Pepsis. So I put in 20 Cokes and I put in 10 Pepsis. And then I did W and E for West and East. So I just flicked a bunch of W's and E's and just went back and forth. And then for C, I did just some numbers. And I tried to have a couple outliers in there. And I tried to end up with an outlier for East, and I tried to end up with an outlier for West. So I want to talk about the bar chart. I'm going to talk about the box and whisker, and then the scaffolded histograms. So just a basic bar chart. If we go into exploration and we look at descriptives, I'll throw A in, and you'll see I have an N of 30. And we can go to our plot, and we can make a bar plot. And when we do that, we'll get Coke and Pepsi, and we'll have our proportions accordingly. We could talk about East and West, and you'll see we have our Wests, we have our Easts. We could do a bar chart, or try to do a bar chart here. Let's see what happens. So it lists our numbers of 1s, 2s, 3s, and that's not really all that informative, although it does give us an idea of the distribution of what the numbers are. We could, when we're dealing with this, take our variable A and we could split by our West and East. We're looking at West and East based on Coke and Pepsi, and we could, at a later time, generate a stacked bar plot. So let me show you how to get to the stacked bar plot, because that is the one that we tend to use when we're comparing. So to get there, you've got to go to frequencies. We've got to go to independent samples. Now, we're trying to compare Coke and Pepsi. So I'm going to put Coke and Pepsi in the rows. I'm going to put East and West in the columns. And you're going to see the Cokes. We're going to see the Pepsis. And so we're having, given the West Coast, given Coke, how many are from West Coast, given Coke, how many are from East Coast. So we have 11 out of 20, 9 out of 20, and so forth. Now, we can generate a stacked bar plot if we want to compare across rows. So we hit bar plot, we go stacked. Now, you'll see that the counts here are not matched. So let's try and get it so that we're talking about percentages within rows, because we're trying to compare Coke and Pepsi from West Coast to East Coast. And we're going to see that there does appear to be some kind of difference. And now we're dealing with percentages. So it's akin to getting a common denominator. And that allows us to look at this line versus this line. Most likely, there's some kind of statistical difference, but it's not far enough apart that I'm going to say for sure. So we will run hypothesis tests based on this data. Now, we just did a stacked bar plot. We went through that process. Let's see if we can't generate a box and whisker plot. So let me see where we need to go for that. So we need to go to data. Nope. Analysis. Yep. Exploration. Descriptives. Okay. Box and whisker often requires some kind of numerical value. So I'm going to throw C in there. And I'm going to click on box and whisker. And we generate a box and whisker. Now we need to split by to get 2 box and whiskers. So let's split by East and West. So now we have our outlier. Here's our West. Here's our East. If you ever need to switch the location of the variables, we go to variables, and you're going to see this little piece right here. And if I flip it, nope, that's not the one I wanted to have it do. I want to click here on B, and I'm going to flip it. Oh, come on. Do I need to have both clicked? I've never done this before this way. Okay. It's not letting me switch that. What did I have to do? So edit, and give me a second. So on edit. Last time I did this, oh, there we go. So I don't want to deal with that. Okay, I want to switch C, and C has levels 1 through that. I would rather have B. There we go. There's my east-west, and I'm going to click on that, and I'm going to say, let's make it that side. And then I hit return, and you'll notice now my west and my east have switched. Okay. Just takes a minute to find and remember how to do all the little ins and outs of Jamovi. All right, so if I'd like to do a stacked, not a stacked, a scaffold histogram, we'll do the B and the C. Let's go to, no, I don't want that right now. I want to go to frequencies. I want to go to independent samples. We're going to go, nope. I want to get my stacked bar plots. I need to do my data. No, analysis. Yep, exploration, descriptives. We'll put the numerical data in our variables, and then we can split by Coke or Pepsi. And when I click on frequency tables, I'll get our frequency tables. I click on histogram, And now we have our scaffolded histograms where we can compare the two. I could change my split by, and I'll pull that out. And this time I'll put my B in. And this time I get an outlier in both of them. And then we can do our box plots. And again, split by, here's our outliers. Our medians look slightly different. The variances look a little different. We could do bar plots. And you can see level 1, we have our split. Level 2, we have our split, and so forth. Okay. Now, keeping our data, let's talk about when we see a difference, or when we're not sure about our difference, or when we're going to look at it and go, oh, there probably isn't a difference, but I'm going to run the tests anyways. The first thing we dealt with was a simulated hypothesis test. And that simulated hypothesis test, what we did was we first had to bootstrap our distribution, because we didn't have a large enough sample to be able to meet the criteria that's required. And if you can recall, the validity constraint, which is the criteria, is you have to have at least 10 successes and 10 failures. So I set up our data to have 10 and 10 for the categorical data. Let me make a quick comment here. When you are dealing with proportions, you are generally dealing with categorical data. And so I put Coke and Pepsi, that's categorical data. I did East and West, that's categorical data. And I did do a numerical list here. I have no idea what these values are. I just picked numbers out of the air and just put them into the Jamovi form. Okay, so you'll notice, however, even though we're talking about categorical data, we're talking about a number, a percentage, a decimal in our null. So we're going to take our null hypothesis, and we're going to say, and we're going to propose that our proportion is 0.8. Okay, so this is the parameter that we are trying to estimate. And we're trying to see, is it actually 0.8? Well, to do a parametric bootstrap, what's going to happen is you kind of pretend it's a spinner, and we have an actual original sample of 30 here. Again, original sample, stretching the truth a bit there. It's a fake sample. I just, put that there. But here sits our box, and it's a spinner. And what's going to happen is 20% is Pepsi, I put it in blue, and then 80% is Coke, I put it in red, just for visual. So this spinner always has a relationship of 80% to 20%, and that 80% to 20% comes from here, this 0.8. Now we're going to spin it 30 times. Where does the 30 come from? Because I have 30 in my sample. If I had 18 in my sample, I would spin it 18 times. Now, to do the analysis, we're going to go to randomize. We're going to do single proportion hypothesis test. We are dealing with the Coke and Pepsi variable. Now, our test statistic is this 0.66. This is our successes. Okay? And we are testing it against 0.8. So I put the 0.8. This is the value that is in my null hypothesis. We're doing a not equals or a two-tailed test. Okay? Our alternative hypothesis is not equals. We're going to go ahead and leave it at a dot plot because I'm just doing 100. And I'm going to seed it. So if you want to do the same thing, you can mimic it. Well, here's what happens. Our p-value is 0.04. All right. So our observed test statistic sits here, and we go an equidistant from the proposed 0.8, and our computer does this. We won't see it, but here's the distance, and then it will do the same distance over here, and then it's going to count from this red line that's not here. Remember, it's not there. We're going to count how many dots are here. We're going to count how many dots are here. So we got 1, 2, 3, 4, 5, 6. Over here, we have, we set our line. It's somewhere in this vicinity. So 1, 1, 2, 3, 4, I'm guessing. And we take the smaller of the two, whichever it is, and we double that, and that's going to generate our p-value. So we got 0.04 out of 100. And so that's how we're getting our p-value on the not equal simulation. So it's telling us, and remember we use alpha is 0.05 as our level of significance if none is stated, none was stated. And we're going to say, we are going to be rejecting the null hypothesis because the p-value is smaller. So p-value is smaller than alpha, reject the null. Okay, so that's a thing we have to have stuck in our noggins. All right, so we would reject the null and we work as if the alternative hypothesis is correct. Okay. Now, if you ask the question, what's the probability of making a type 1 error in this situation, it would be the same thing as our alpha. Our alpha is 0.05. I didn't put the 0 in the front, so forgive me. So it's 0.05. This is the probability of making a type 1 error, and we recognize that that exists. Okay. So how would we do the bootstrapping for our confidence interval? All right. Well, we're going to do single proportion confidence interval. I'm going to click on it. We want the 95% confidence interval. Now, here's what happens. We take our A and we put it in and we bootstrap. Well, again, I'll do the seed here. So what happens is it takes the data that we have. So remember, we had 20 Cokes and we had 10 Pepsis. And we are going to repeat samples again of size 30, but we're going to pull our samples from the data that we have. We don't have a proposed value. That's why it's not called parametric bootstrapping. If we have the proposed value, it is parametric bootstrapping. And we repeat our sample of size 30 with replacement over and over and over again 100 times until we get this distribution. Now, if we're going to do the 95% confidence interval, it's going to do the 2.5 percentile and the 97.5 percentile. And it gives us our lower and it gives us our upper. So our 95% confidence interval is containing our value of 0.8. Okay, so based on our value of 0.8 being contained in here, we would support the null hypothesis, and we would keep and operate as if the 0.8 is reasonable or plausible. Okay, so there is, reminding you, there is the possibility that they don't tell you the same story, but most of the time they do. And because we did a two-tailed test on the previous with an alpha of 0.05, our confidence interval stays at 95%. Okay, so they again can tell us different stories, and that how to deal with that is another topic. We don't deal with that in this class. All right. So we just showed confidence interval hypothesis test for one proportion. Now what happens if we're doing a two proportion? All right. The null hypothesis in a null, when we're doing two proportion, is going to be P1 minus P2 equals 0. And for our example, we're going to do not equals 0. So our HA would be P1 minus P2 does not equal 0. Okay? And what we're doing right now is we're simulating the two proportion hypothesis test. So let's go back to our data. And we have Coke and West. So we're going to do that sort of study where we have is Coke preferred in the West Coast more, or that kind of thing. All right. So we're going to do randomize. We're going to do two proportion hypothesis test. Our rows will be Coke or Pepsi, and our columns will be location. Okay. And we are trying to compare rows. Actually, let me think about that for a second. I have to flip this, and I'll explain in a second. So the does location, so given location, Coke or Pepsi. So our location should be in the rows, and our Coke and Pepsi should be in our columns. Okay. So given East Coast, do they prefer Coke? Given West Coast, do they prefer Coke? And then if we talk about the stacked bar plots, so give me just a second here. I will go back. East-West is in there, so just for fun, we will go back, and I will put East-West in the rows. I will put that in the columns. Okay, so that gets us our same situation that we had. We're going to bar plot, we're going to stacked, we're going to go percentages, and we're going to go within rows. And now we're looking at location, and we're looking at Coke and Pepsi. So the West Coast appears to prefer Pepsi over Coke more than the East Coast does. Okay, East Coast seems to prefer Coke more than Pepsi. And so if we compare the two, there does appear to be a difference. So let's go back to our randomize, two proportions hypothesis test, location in rows, and then so given location, do they prefer the Coke? We're going to randomize. So here's our test statistic. The difference in proportions 0.23. I don't see us getting a significant difference, but we'll go through it anyways and talk about it. So let's do 1,000. Why 1,000? Just to see how we deal with it instead of the dot plots. So I did the histogram. What'll happen again? Here's our 0. Where does the 0 come from? The 0 comes from our null hypothesis of 0. Okay, and we have an observed difference, which is an observed difference of 0.239. They're going to count the number of observations this way. Okay, then they're going to go the same distance over to here, and then they're going to count the number of observations this way out into the left tail, and then they're going to take the smaller number of the two and double it, and that will generate your p-value. So we have a p-value of 0.32. So the p-value of 0.32 is saying fail to reject the null. So if the p-value is larger than the alpha, we fail to reject the null. And so in this instance, we're keeping the null and we're scrapping the alternative. It doesn't seem like that there is enough evidence to say, yeah, the East Coasters prefer more Coke or the West Coasters prefer more Coke, kind of thing. All right. So that's a two proportion hypothesis test. Let's do a two proportion confidence interval. So we're going to do the two proportion confidence interval. We'll click on that. Our rows will be the location, and again our columns will be our drink of choice, Coke or Pepsi. And we can do 100 simulations. It's helpful to see the dots, so I'll do that real quick. All right. So our confidence interval, when we do 100 simulations, now let me back up for a second. Here's what happens. So we're going to take the data we're going to deal with the East Coast. And if location doesn't, I'm sorry, given East Coast, given West Coast, if location doesn't matter in terms of preferring a drink or not, then what's going to occur is this Coke and Pepsi should have no the drink of choice doesn't matter. So this value here could be 6 and this value here could be 5. And what we keep doing is we take and bootstrap this information over and over and over again. And we bootstrap this information over and over and over again. So what will happen is that we take the 11 and we have 2 and 9, and we with replacement. So you can get more than 2 Pepsis, but you draw 11 total East Coasters, and you place how many Cokes and how many Pepsis, and you do this with replacements. So in your little hat, you have 9 Cokes, 2 Pepsis. There's a total of 11 in there. You're going to reach in, pull out, and you'll go, oh, and you'll write down, is it a Coke or a Pepsi? And then you put that draw back in the hat, and you do this 11 times. Same thing with the West Coast. And what you do is you compare those differences, or those percentages, by doing a difference. And this is all of the possible differences that occur when we did that bootstrapping. Okay? So what we get for our 95% confidence interval is the lower being negative 0.14 and the upper being 0.53. And so our confidence interval contains the 0. The 0 sits in between. So the 0 that we're talking about here is the 0 that we're talking about here. This 0 that I'm circling is this 0 that I'm circling. And so our confidence interval is saying, yeah, there isn't a difference between them. And so our confidence interval is supporting our null hypothesis as well. Now, most of the time when we did this, we did it by a histogram. And so even when we did a histogram and we went to 1,000 draws, we were still reasonably close to what we had before. We just get a little bit better distribution. It looks more symmetric than it was before, etc. Now, I'm going to make a comment. There was a question on one of your homeworks, and it does connect back to the fact that, oh, I'm in the wrong spot. I'm going to ignore me for that. Just block that out of your memory. Okay, so we've done simulated 1 proportion, simulated 2 proportion, and we've done it for both confidence interval as well as for hypothesis test. I hope that makes sense. Now, let me talk about this idea briefly about this central limit theorem. So this central limit theorem idea says that when we've simulated or drawn or done every possible difference or every possible draw that could occur, we get a normal curve. But that entire group of samples is called a sampling distribution. And the thing is this is a sampling distribution. It's not a complete one. They're saying that when we're talking about the theoretical model, they're saying the complete one. And what happens is there's 2 things that occur. The mean of the sampling distribution is always equal to the mean of the population. And that's nice because in terms of the z-score, the second term in the z-score drops out or we have access to. Okay? It also gives us our standard errors. So our standard error is in the denominator of the z-score. So just give me a second here as I go back to draw, and I'm going to draw, and I'm going to write the z-score formula idea down. So the z-score here is the raw data point, or it is the sample mean that we're looking at, or it is the sample proportion that we're looking at. So it's a raw data point, it's a test statistic, minus the mean. Now, this mean can be the mean of just a raw piece of data, and so it can be x bar, it can be mu, and if you're dealing with the central limit theorem, what it looks like is mu sub x bar, or it's going to be mu sub p hat, or mu sub p hat difference. And this piece here is just equal to the mean of the population, and this piece here is just equal to the percentage or the population proportion. And again, remember, your book likes to use pi in that place. Okay? And then it's divided by the standard deviation or the standard error. Now, the standard error formulas. Okay. So if you are working with the sampling distribution of sample means, then your standard error is sigma divided by the square root of the sample size. Now note, we haven't done anything with that yet. It's not going to be on the quiz. So it's just being aware that it exists. Okay. If you're going to deal with the mean of the p hat, then your standard error in that situation is the square root of p q divided by n. And I know I keep saying this, but that's really, the q is 1 minus p. Okay, so if p is 0.6, q is 0.4, right? If you're dealing with the standard error for a confidence interval, and you're dealing with, and I'm going to denote it this way, so you're dealing with p hat and you're dealing with the difference. So I'm going to write difference here. For the hypothesis test, remember, we get this pool going on. So our p hat pool is x1 plus x2, and if you're putting it into your calculator, make sure that's in parentheses, divided by n1 plus n2. And again, if you're putting that into your calculator, we got parens there. So that's p hat pooled, and then q hat pooled is the 1 minus the deal. So what you're going to get is p hat pool. Then you're going to get q hat pool. And then 1 over n1 plus 1 over n2. So there's your standard error if you're dealing with a hypothesis test, and you are getting the z-score for that hypothesis test. Okay. Now I have to scroll down here somewhere and find where my cursor is. Just a second. There we go. Won't let me go farther, go farther, go farther, go farther. So what happens if I need to get the standard error for a confidence interval rather than for a hypothesis test? All right. So first of all, again, you need to make sure it meets the validity constraints. And again, I made the comment that our data is set up so that we have at least 10. We have at least 10 Cokes and at least 10 Pepsis. We have at least 10 Easts. We have at least 10 Wests. And so the standard error, when we're dealing with the difference in two proportions, okay, so this is going to be P1 hat, Q1 hat, N1, and then plus P2 hat, Q2 hat, and then N2. And so what's going to happen when you're dealing with the confidence interval here, you're going to get P hat diff. So you're going to take your test statistic. You haven't made it a z-score, it's just P hat diff. And then plus or minus. And then you have that z-score multiplier, which in the 95% case is 1.96. And then this piece here is your standard error formula. Okay. Now, saying that, you can get a confidence interval for one proportion based on theoretical. The validity constraints are that NP and NQ have to be greater than or equal to 10. If we take our 30 and hold on. Yep. So as long as we're greater than 10 in this situation, we're okay to go forward. Just had to get to the right spot in my brain there. So the standard error in this case is going to be the square root of P hat Q hat over N, because we only have one sample to deal with. So we've got P hat plus or minus our special z-score, and this is our test statistic, multiplied by square root of P hat Q hat over N, and again this is our multiplier right here, so it's a 1.96, it's a 1.645, and so forth. Okay. And so we establish our null hypothesis, just like we did, and then for the we run our simulation like we showed, and then we can do confidence intervals as well, as long as we meet the validity constraints. I hope I didn't drop anything off. Okay. Just thinking. So, standard error z-score. What's a z-score? Z-score is this formula, and it is the number of standard deviations away from the middle that we're dealing with. Not sure I can come up with a quick example for that to show you how to deal with it. Okay, so a z-score. Let's see what we got here. Suppose our null is the following. We're going to draw. We're going to say the null is that the proportion of West Coasters minus the proportion of East Coasters, they're the same. So we're going to go equals 0, and then the alternative, and we'll just make it easy on ourselves, and we'll say East Coaster not equal to 0. So we'll do a two-tailed test. All right. To get our z-score, we're going to get our difference. Let's see if we have our difference still presented. Traveling back here. Difference in the two proportions. Here it is, 0.239. Okay, so that's our test statistic. So that's the thing that's going to be in the top left, 0.239. Now, the 0, that's from the null hypothesis, is going to go there. The thing is, now we got to get our p hat, which we go here. We need our pooled. We need to generate our p hat pooled, and then do p hat pooled, q hat pooled. So give me a second here. So 9 out of 11 and 11 out of 19. So let me write these down. So I have 9 out of 11 and 11 out of 19. So that's our first. And then um, 11 out of 19. So we have 20 out of 30. That is our p hat pooled. Again, just show you where I got that from. So 9 out of 11 and 11 out of 19. And then based on our formula, it says add the x's and add the n's and then divide. So my p hat is going to be 0.6 repeating. So I'm going to go 0.67. Just it's 0.6 repeating, but I'm going to use 0.67 as a good approximation. So now I'm going to have the square root of 0.67 multiplied by 0.33. Remember, these two have to add up to 1. Even though I'm multiplying them, do catch that I'm multiplying them. And I'm going to have 1 over 11 plus 1 over, whoops, I made a typo here. This is supposed to be a parenthesis. This is supposed to be a parenthesis. It's underneath the square root is what I was thinking, and I just dropped that off. So 11 or 1 over 19. Okay, now I'm going to punch this all into my calculator, and I'm going to get a z-score. So my home, clear, 239, minus 0 is just 0.239, divided by, second, the square root of 0.67 times 0.33 times parenthesis 1 divided by 11 plus 1 divided by 19. Close that off and give it a second paren to make sure that paren is underneath the square root. And I get 1.34 as my z-score. All right. Now, sorry, folks. What that's basically telling me is that when we go to the standard normal curve, now the standard normal curve is set up so that the 0 is in the middle, and then the 1 is 1 standard deviation from the population distribution, okay? And it's been transformed. So what's going to occur is we take this 1.34, which is about here, and because I said we're doing a two-tailed, we're going to do it on both sides. And over here is our negative 1.34. And we're going to do second VAR's normal CDF. And since we are on the central limit theorem, we're using the theoretical. The central limit theorem means that we have the normal curve, the right side and the left side are symmetric. It matches. So what we're going to do is we're going to take negative 10,000, really our negative infinity, and we're going to go to negative 1.34. And remembering that our mean is 0 and our standard deviation 1 is 1 in the standard normal curve. All right. And we go second VAR's normal CDF. So just a second. I'm using my 89, which is very different than using the 84. It takes a minute to get to wherever you want to get to. So give me a second here. There we go. Normal CDF. The lower is negative 10,000. The upper value is negative 1.34. Enter, enter. So I'm getting a left side p-value of 0.09. But remember, we have to double that because it's a two-tailed test. So I'm going to get 0.09 times 2 because of the two tails, and I end up with 0.18. This value is greater than 0.05, so we are going to fail to reject the null. And so we are failing to reject the null, we are keeping the null, and we are scratching the alternative. Remember, that is supposed to be an E there, even though it looks like a C at the moment. Okay. I feel like I dropped something off in there somewhere, but I'm hoping that you see what a z-score is, how do we use it, the p-value, theoretical proportion, and so forth. Hopefully it makes sense. I hope. Anyhow, you guys have a good rest of your day, and I will post this and send this out to the classes. All right. Have a good day.